Hello, welcome back. We're going to continue on with our interval of convergence for a power series. And so before I get to the three examples I want to do in this video, I just want to show you the three cases that we talked about in the previous example. The first case that we did was where it was one single point. And so you can look back at the previous video to show the example where the radius is 0. And it literally is where x is equal to 0. So the series converges only at C, and that's where x was equal to 0. The second example that we did was this crazy one down here, so we'll get to that in a second. The third example that we did last time was that the interval of convergence is for all real numbers, so negative infinity to positive infinity, and then our radius would actually be infinity. And the one that we're going to talk the most about, the more common one, is what happens when we actually have an interval of convergence that is not all real numbers or x equals 0. And so what we do with this one is we actually have to find that interval. I'll talk more about the radius today in this example, and then we have to check whether our endpoints actually converge or diverge as well. And you can see clearly here are the four cases where neither of them, both of them, the left one does, and the right one does. So I've got three examples that I want to show you guys for this example for this video, and so let's get to it right now. Okay, so our first example that we want to do is right here, and the question's asking us to find the interval of convergence for this example. One of the things that I want to say really quickly about this example when we start out first is that when I do the limit, alright, so when I actually try to find the interval of convergence, remember that the first thing that we do is we take the absolute value of our function, right? And so all this is going to do here is it's going to change the sign from positive to negative, negative 1, back and forth, right? So what I can now do with this problem is that this actually can go away initially. It will come back into play a little bit later on. But when I'm actually trying to find the interval of convergence, my focus actually right now just has to be on what's right here. So I'm going to kind of disregard this right now. And again, it's because I'm taking the absolute value of this entire series. And again, this is going to cancel this out. All right. So it's just changing our signs. So when I actually start the problem, the first thing that I'm going to do is I'm going to do the first term, right? That precedes this one right here. And then I'm going to divide by a sub n. Right? And so this is our a sub n in the equation that we used in the last video. And so again, that's our value of this. And remember that this has to be less than 1. So that's our series. And this, in order for this limit to converge, this limit has to be less than 1. So we're going to continue on with what we did in the previous examples. And we're going to go ahead and write the limit as n approaches infinity. And then this is going to be n plus 1 all over n. And then I'm going to multiply by x plus 3 to the n power times x plus 3 all over x plus 3 to the n power. What I did there really is just I just grouped them right together. I grouped the n's together and then the x's together. And in that case right here, I'm actually able to cancel out this right here. Because remember, everything's being multiplied together here. So this is the multiplication for this. And again, this must be less than 1. And so when I start simplifying a little bit more, I get the limit as n approaches infinity of n plus 1 over n times x plus 3. Right? Okay. So what I need to now do in this problem is I need to look at the fact that this right here, this little piece right here, this limit's going to go to 1, right? Because we have the highest degree in the numerator equal to the highest degree in the denominator, and the ratio of their coefficients is 1, so this is going to be 1, and so I'm going to be 1 times x plus 3, right? And this has to be less than 1, right? This has to be less than 1. The absolute value of it has to be less than 1. So then what we can do for this, in order to find the interval of convergence, is we take the x plus 3, and we set it between negative 1 and 1, and we get that x must be between negative 2 and negative 4, right? Negative 2 and negative 4. So we go ahead and write those things down. So with that, you can see that the center is going to be at negative 3, and that the radius is actually going to be equal to 1, right? So if we're at -3 and our endpoints are at -2 and -4, right, then we see that the radius here, this radius is going to be equal to 1. So the center is at -3 and the radius is at 1. What we must now do is figure out whether or not we need to include the endpoints to our functions. It's open bracket or closed bracket. And this is where we actually go back and look at the entire original. So we actually want to look at this whole thing right here as a whole. So if I plug in -4 to this, right, I plug in -4. The one thing that we'll say about this really fast is this is an alternating series, right? So if I plug in -4 to x, and these, by the way, these are x values, right? These are x values, so we don't care about the n's. We're going to get n. So what I do down here is just, okay, when x is equal to -4, I plug in n times -1 to the n power, right? -1 to the n power. And so with this problem right here, you will see that this is an alternating series test. So in order for this to converge, it has to pass the fact that the limit has to be equal to 0. Well, this limit clearly does not equal 0. This limit is going to go to infinity. So this is going to diverge. And the same thing when x is equal to -2, right? We're going to have the same thing when x is equal to -2. We're going to get n times 1 to the n, right? So this is basically just going to be n, and so the limit as x approaches, or n approaches infinity of n is just positive infinity. So since both of these limits does not equal 0, then I can say through the alternating series test that they're actually going to diverge. So our interval of convergence for this problem is actually going to be -4, -2, not including the endpoints. Okay? So let's continue on with our second example and see what we can do with that. One of the things that I encourage maybe you guys to do is to pause the video and see if you can try it on your own before I do it, but let's just see what we can do for this problem now. So the first thing we're going to do is we're going to find the limit as n approaches infinity, and then I'm going to get to the point now where I'm just going to start doing this term, the x to the n plus 1, is just x to the n times x to the first, right? There's really no need for us to do that. And then it's going to be n to the first to the 1/2 power. And again, just like previously, if I'm going to divide by the original term, I can multiply by the reciprocal of this. And so I will do that. And so if you look at this problem now, I can go ahead and I can cancel out these two problems here. So we can continue on and find the limit as n approaches infinity of n to the 1/2 over n plus 1 to the 1/2 times x. And you guys will see the more I do these problems, the more I group the n's together and then the x's together. Because really I'm looking at a limit as n approaches infinity. So this right here tells us a lot about what x can and cannot be. Because I know that this right here, if I just look at this little piece of our puzzle, it's okay, well, I know this limit right here. This has to equal 1. Actually, it does equal 1, because the highest degree in the numerator is equal to the highest degree in the denominator. And so I'm able to say that the coefficients in front of them would be 1. So I know that based on previous examples that x must be less than 1, right? The absolute value of x must be less than 1. So we can now say that x must be between -1 and 1. So we have, like the previous example, we have the interval of convergence is -1, 1. So our center would be halfway between the two of them, which would be 0, and the radius in this case would equal to 1, right? So what we must now do is we have to check our endpoints and see whether or not they're included in our intervals of convergence. So the first thing I'm going to do here is look at when x is equal to -1. So I'm going to plug in -1 to x, right? And this is my little side work. You know, technically I should have the proper notation for it. If I ever ask you to check the endpoints, you probably should do that. When x is equal to -1, you're going to get this actual function. And so when we look at this series, we can say that this is an alternating series. so we can look at whether two conditions hold true. It does the limit as 1 over n to the 1/2 as n approaches infinity equals 0, and yes it does. And then is my second term less than my first term? Is my series decreasing as I move through? And you can also say yes, this is true. So even though I would go and say this conditionally converges, it actually converges. So I would include -1 to this. And so I was able to do this by the alternating series test. Okay, and there's a video on that if you need a little refresher on it. But using the alternating series test, I can say that this series actually conditionally converges. And since it conditionally converges, we include it in our endpoints. All right, and then let's look at when x is equal to +1. Well, that's just going to be the summation infinity of n equals 0. And so when I plug in 1 here, well, it's just going to be 1 to the n, which is just going to be 1, and it's going to be n to the 1/2. So this is a p-series. And you guys realize that since this is a p-series test, remember that in order for a p-series to converge, then our exponent has to be greater than 1. It's less than 1, so I know that it's not going to be included. So then I know that our interval of convergence for this series is going to be -1 to 1, including -1. And a lot of times you will see that they'll add, just a little n right there for equals to. So there's 2 ways to write that problem.